Hello everyone, so this video is going to be about introduction to probability for Maths Methods 3 and 4. Okay, so Maths Methods 3 and 4 is divided into 4 parts: discrete probability, binomial distribution or Bernoulli sequence, normal distribution and population sampling. And I will be making videos for all of these 4 subtopics, so stay tuned. And also I have included like couple of exam style questions in this video so that you get into the groove of what's going to happen next. Anyway, let's start off by recapping some important notations, which is A union B is a notation to represent the event that is in set A or set B. A intersection B is a notation to represent that event is in set A and set B. And A dash basically means every other data set or every other event that is not in dataset A. If this did not make any sense to you, don't worry, I have some examples to make myself a bit more clear. So, if A equals to 0, 1, 2 and 3 and B equals to 2, 4, 6, 8, 10, then solve for A union B. So again, A union B is an either or situation. So that means we have to include every single number that is present in A or B, which is just going to be every number over here, except we don't repeat numbers. So our answer would be 0, 1, 2, 3, 4, 6, 8 and 10. A intersection B, or in other words a common digit or a common thing between dataset A and dataset B. Well, there is only one clear common number, it's just going to be 2. So our answer is just 2. A dash again is just every other number that is not in dataset A, meaning it's just going to be 4, 6, 8 and 10. Again, we can't include 2 because 2 is also present in dataset A and we want every number that is not in dataset A. So next move on. B dash is just every single number that is in dataset A and not dataset B. So it's just going to be 0, 1 and 3. Again, we cannot include 2 because 2 is present in both datasets and we only want numbers from dataset A. So that's one question done. And this is another question which is very similar to what we did above, except it's just a bit more wordy. So let A be the student who like chess and let B be the student who like badminton. Then we have to write probability expressions to represent the prompts as follows. Students who like chess but not badminton. This can be worded again as student who likes chess and not badminton. So students who like chess is just A, and whenever there is an and, 99% of the time is going to be an intersection, and whenever there is an or, 99% of the time it's going to be union. But again, read the question twice or thrice just to make sure that you do not make the mistake. So students who like chess but not badminton. So but not badminton is B dash. Student who dislikes chess and badminton. So A dash intersection B dash, because there is an and over here. And students who likes chess or badminton, it's going to be A union B. And students who like chess and badminton is going to be A intersection B. Okay, so let's now move on to learning these new concepts of mutually exclusive independent events and dependent events. So what is mutually exclusive? Well, if 2 or more events cannot occur at the same time, they are said to be mutually exclusive events. So let me quickly give you a visualization of this using a Venn diagram. There you go. So here is a Venn diagram of 2 datasets A and B. Now you can clearly see that there is no intersection between these two, and this is what mutually exclusive represents, when 2 things cannot occur at the same time. So what does this information tell us about relevant formulas in probability? Well, if the 2 events are to be mutually exclusive, then probability of A including B is just going to be probability of A plus probability of B. Now, how is that? So, well, if I were to ask you what is probability of A including B, you're obviously looking at this section over here, right? Since there is no intersection between these two, we can clearly just, omit that part out. So the only part that remains is going to be this and this. And therefore, probability that A including B is just going to be probability of A plus probability of B. Now, other thing that it tells us is that probability of A intersecting B is just going to be 0. Pretty self-explanatory here, because there is no intersection between A and B. well, the probability of A intersecting B is just going to be 0. Okay, I hope that made sense. Now, let's move on to independent event. What is independent event? Well, if the outcome of one event does not affect the outcome of other events in the sequence, it is said to be independent event. So, let me use a tree diagram to give you a visual of what this scenario is. So, supposingly, you're tossing a coin. The two possibilities are heads and tails. An unbiased coin, so heads and tails. And if it's unbiased coin, what is the probability that you toss a head? 0.5. And what is the probability that you toss a tail? 0.5. Now say that you are tossing this same coin again. So there's going to be two more possibilities, head and tails. What is the probability that you land a head on your second try? It's still going to be 0.5, right? And same with the tail, it's still going to be 0.5. So you can see that no matter how many times you toss this coin, the probability of landing a head does not change at all. And this is an example of independent event, where the outcome of your first toss does not affect the outcome of your second toss. Alright, now what does this have to give you in terms of formulas? Well, probability of A intersection B is going to be probability of A times probability of B. This is true for all independent events. Okay, how do I use this formula in this context of, tossing the coin? Well, say that you are finding H intersecting T, probability of H intersecting T. So, we are looking at this branch over here, H intersecting T. So, what is the probability of rolling a H? In the first go is just 0.5. Now, because it's a tree diagram, we times it by the second branch, which is also 0.5, and this is going to give us 0.25. Alright, so this is an example of independent event. Now let's move on to learn what dependent event is. So dependent event is when the outcome of one event affects the other events in the sequence. That is known to be independent event. An example question on this could be that, well, if the probability that it rains today is going to be 0.5, and the probability that it rains tomorrow, if it rains today, is going to be 0.1. So the probability that it rains tomorrow is dependent on probability if it rains today. If it rains today, the probability that it rains tomorrow as well is going to be 0.1, and if it doesn't rain today, well, it's going to be 0.9. Something like that. This could be a question that could pop up using the concept of dependent events. So the formula that is relevant in this event is probability of A intersecting B is just going to be probability of A times probability of B given A. Well, I'm going to just rewrite this formula. Maybe it will ring a bell for you. If it doesn't ring a bell, well, this is the formula for conditional probability. And don't worry, I'm going to briefly cover that topic in today's video, as well as going to attempt exam style question based on conditional probability. So stay tuned for that. Alright, now let's look at visualizing the Venn diagram. So this is going to be a pretty simple task, I hope, because this is just a small recap from methods 1 and 2. So this section over here, this entire section is just going to be A intersection B dash. Pretty self-explanatory. Now this middle one is just going to be A intersecting B, and this part is just going to be A dash intersection B. I hope this wasn't too hard for you to understand. And this outer section here is just going to be A dash intersecting B dash. Alright, so this is your basic visualization of Venn diagram. Alright, so using this relevant concept and visualization of Venn diagram, you can proceed to derive this equation that is mentioned in your Maths Methods textbook as well. So let's quickly start off by identifying this proportion of Venn diagram. So this one over here would be PR of A intersecting B dash plus PR of A intersecting B plus PR of A dash intersecting B plus PR of A dash intersecting B dash. Now adding all of this up would simply just result in 1, because that's how probability works. So if entire Venn diagram is shaded and you're meant to find the probability, well, it's of course going to be 1. So this all result in 1. Now what I'm going to do is simply rewrite the equation to proceed further. Okay, next what I'm going to do is I'm going to break these two terms down further. So let's see if we can do that. So again, let's start off by identifying these regions of Venn diagram. This is going to be PR of A dash intersecting B plus PR of A intersecting B, and this would give us probability of B, right? So I can rewrite this whole equation as, okay, now let's see if we can break this one down further. Of course we can. So as we can see that this shaded portion here is PR of A union B, and this shaded one is PR of A dash intersecting B dash. And again, if we add these two proportions up, the probability is just going to be 1, because again the whole Venn diagram is just shaded. So we can now write our equation as, alright, now we can also cancel these two terms off, of course. So that would leave us with, okay, now what I'm going to do is to try break this term down further so that we can include PR of A in our equation, because that's pretty much the whole only thing that we are missing here. So we can again identify this region, so PR of A intersecting B dash plus PR of A intersecting B is equals to PR of A. Now we have both of these terms over here, this one and this one. So what we can do is simply make this term over here to eliminate it from the main equation right there. So let's do that real quick. Okay, now we can substitute this part into our main equation, and that will give us our answer. So okay, and this is your equation proved. Alright, so let's now talk about probability table or Karnaugh map, whatever you want to call it. So how this works, so again, this is a concept from math methods 1 and 2, so I'm going to briefly go over it. But anyway, so if you want to find a probability of A intersecting B, you would have to look at this box over here. If you want to find probability of A intersecting B dash, this box over here, so on and so forth. Now one other thing that is relevant in this table is that when you add these two values up, you will get probability of A, and then when you add these two values up, you'll get probability of B. So you can add horizontally and you can also add vertically, but you cannot add diagonally. That's not how it works. But make sure that all your probability adds up to 1. So PR of A plus PR of A dash would equals to 1, PR of B dash plus PR of B dash equals to 1, and so on and so forth. So that's the basic gist of Karnaugh map, and let's quickly do a question on that real quick. So Daniel studies every day as he's in year 12, of course. The probability that he will study math methods at night is 0.4. So M here in this context is for studying math methods. I'm going to write 0.4 as his probability. The probability that he will study English is 0.1, so 0.1, and the probability that he will study both subjects is 0.03. What is the probability that Daniel will study English but not math methods? So study English, yep, so this block, but not math methods, and they intersect right over here, so I'm going to call this one X. Okay. Now what other value do we know in this Karnaugh map? Well, we know that all of this adds up to 1, so this will be 0.6 and this would be 0.9. Alright, but I believe this is the only information we need, so we can say that 0.03 plus X equals to 0.1 and X would equals to 0.07. So this is the probability that Daniel will study English but not math methods, and that would be 0.07. Alright, now what is the next question? What is the probability that Daniel does not study at all that night? Well, so does not study at all, meaning he does not study English, nor does he study math methods, and they intersect at this block, so I'm going to call it Y. Now we only need a couple of information and not the whole Karnaugh map to figure this one out. So we know the value of X over here from above, so we can fill that in real quick, and we know that this is going to be 0.6. That's all we need to figure out this question. So we can say 0.07 plus Y equals to 0.6, and therefore Y equals to probability of him not studying English or math methods, English and math methods, is going to be 0.53. And that's how you tackle this sort of question. Now they are quite common in VCA exams, but this sort of questions are kind of on the easy side. But yeah, It's quite important to know. Alright, now let's quickly look at conditional probability. So conditional probability is a scenario that involves calculating probability of an event given that another event has already occurred. So an example of this would be, well, find the probability of it raining today given that it is cloudy. So in those kind of situations, conditional probability is applied. So what is the formula of conditional probability? Well, conditional probability is same as writing probability of A given that B has already occurred. So what is the formula now? Well, probability of A given B is just probability of A intersection B divided by probability of B. However, if the events are to be independent, what would it be then? Well, the formula of it doesn't change. The formula is still going to be A intersection B or probability of B. But we know that this probability of A intersecting B in an independent event can be simplified to probability of A times probability of B and divided by B here, which comes from there. So now we can cancel these two out, leaving us with just probability of A. If the events are to be independent, then probability of A given B would be the same as probability of A. Alright, so let's quickly go over this exam question that involves conditional probability and also merges the concepts we learned today all together. So a pencil manufacturing company has 3 factories A, B and C respectively. 42% pencils come from factory A, 30 from factory B, and the rest come from factory C. So 28% come from factory C. The owner claims that probability of faulty pencil is 0.08, 0.1 and 0.05 from factories A, B and C respectively. Alright, draw a tree diagram to demonstrate this scenario. So let's quickly jot down some numbers. So the probability that the pencil is made from factory A is going to be 0.42, from factory B is going to be 0.3, and from factory C it's going to be 0.28. So let's quickly draw a tree diagram. So A, B and C, A, B and C. So probability from that a pencil is made in factory A is 0.42, from B is 0.3, and from C is 0.28. Now probability that it is faulty and not faulty. So for probability that it is faulty and from factory A is 0.08 and this would be 0.92. From factory B is 0.1 and this would be 0.9, and from factory C it would be 0.05 and 0.95. Okay, so this is your tree diagram done and dusted. Alright, so now we have to calculate the probability of pencil being faulty. What we have to find is just these branches. So probability of A and faulty, B and faulty, C and faulty. There you go. So since it's tree diagram, we can just simply multiply these values, add them up and find the probability. So probability of it being faulty is just going to be 0.42 times 0.08. This is for factory A, plus 0.3 times 0.1, this is from factory B, plus 0.28 times 0.05, this is for factory C. Now multiplying and adding it all together would result in 0.0776. This is the probability overall that a pencil is faulty regardless of what factory it comes from. Okay, calculate the probability of pencil being selected from a factory B given that it was faulty. So probability that it is selected from factory B given that it was faulty. Now again we will just write the formula. So probability of B intersection faulty divided by probability of faulty. Okay, now this term right over here just means this branch right here. So probability of B given that it's faulty, so it's going to be 0.3 times 0.1 as shown on this branch over here in yellow, divided by probability of faulty. So probability that we calculated, probability of pencil being faulty that we calculated in part B is 0.0776, and if we were to simplify this we would get a probability of 0.387, and there you go, that's your answer. Okay, so this is the end of the video, and thank you all for watching. First of all, I hope you found it interesting, enjoyed it and learned something from that, and I'll see you next time.